In this video, we're going to add our first major feature to our interpreter. We're going to make it so that we can assign variables with names and then refer to those variables by their names in later expressions. So, as with the example shown here, we could make a variable called a, assign the value 5 to it, and then use that variable a in a expression after that and have it work the way we expect. So in order to do that, we're going to have to make a bunch of changes to our interpreter. But first, we're going to change the parser to support the two situations where we use this new feature. We're going to have to handle identifiers, and we're going to have a rule for when a variable is referenced, and we're going to have to handle assignment. So let's go ahead and do that. So here's our calculator program. And let's go ahead and open up the parser. So, as I said, there are two cases here, and we have to add both of them to our data structure. So first we have name references, which we'll deal with a constructor called name, and a variable is named with a string. And then we need to handle assignments, which is just a binary operator like all these others. So assign calc expr. Now, it would have been possible for us to go assign string calc expr, and then this would enforce at parse time that the thing on the left-hand side of a assignment expression has to be a variable name. But if we just make both sides be a calc expr and then handle validating the left-hand side of the expression at evaluation time, that means we can reuse the name rule, which is a little bit simpler. So once we've added those two cases to the data structure, then we need to add them. Well, we need to add the name case, or we need to add the operator to the op table. And we do that just like any other binary operator. Binary equals assign. So we're putting that at the end of the list so that it can have the lowest precedence, because we want to do the arithmetic to calculate the value before we actually assign the value of the variable to the variable. If we set equals to have a high precedence, then it would be harder to figure out what was going on. So then there's one more thing we need to do, and that is actually handle this, handle name references. So let's put in a name expr, and a name expr is another one of these guys. So we have to pull out the name, which is many one letter, and then it's some spaces. And then finally we need to return the name with the name. And we don't have to do the read thing that we had to do for the number expression, because conveniently we wanted a string. A string is what we actually got from the user in this case. So unless I forgot something, that should be all the pieces. Let's give it a try. So parse calc expr a equals 5. Okay, so the thing that I forgot is that I have to actually do something with that name expression thing that I put in. So let's put it in the same place that number expression is. Here in paren expr, it's either that we have a parenthesized expression, or we have a number expression, or we have a name expression. So now when we try it, it should actually work. So parse calc expr a equals 5. And this time it does the right thing. We have an assignment. The left-hand side of the assignment is a name a, and then the right-hand side of the assignment is a number 5. So if we do a more complicated expression, it'll still do the right thing. So we're assigning to the value a, or to the variable a, and what we're assigning is the sum of the previous value of a and this product of 3 and 7. So let's go back to the slides and see what's next. So after we have the parser working the way we want it, we're going to have to change the evaluation function, which is a little bit more difficult. So the hard part here is that when we evaluate a equals 5, we've assigned a value to a, but we have to keep that mapping of variable names to values somewhere. And we need that to last across separate prompts. Right now we have no state between separate prompts. If you type in one expression on a line, then it won't remember anything about that expression when you type the next expression on the next line. And if we're going to have variables, that's not good enough. So what we need to do is have an environment, which is the technical term for a mapping of variable names to their values in a programming language. And we need to actually pass that around in the program, even between different calls to evaluations of the of expressions that users are typing in. When a user types in an expression, we need to update the environment if they've assigned any variables. And then for the next expression that they type, we need to still have that. So, like I said, an environment is a mapping of variable names to their values. In all the programming languages that we're going to be working with in this class, and in most of the programming languages elsewhere, variables normally live in a whole bunch of environments, which are sometimes referred to as scopes. And you can actually have different variables of the same name in different environments. But for our calculator right now, we're just going to go ahead and add one environment. So if you use the variable a, that's the only variable a that can exist in one run of the calculator. And the way we're actually going to implement this map is just as a list of string, comma, int tuples. And that makes like the various operators that we want to do relatively straightforward. So let's go ahead and implement that data structure for the environments. So here's the existing calculator without variables. And we'll just go ahead and add our data structure functions for environments up at the top. So an environment is a list of string int pairs. The empty environment is the empty list. To delete a value from an environment, which I'm typing first because we're going to need it for adding, since we want to replace things, and so we want to take out the old value. So if we have an environment and a name, then what we need to do here is we need to filter out any pair with the with that name from our list. So we can actually type the environment as x:(xs). So then we need a base case, since we're going to be doing recursion here. So the base case is the empty list. And if we delete from the empty list, we get the empty list again. So if we don't have the empty list, then the question is whether the x that we're looking at is the name that we wanted. So actually, instead of calling this x:(xs), let's call this nn, vv, and pattern match the environment entry. So then we can say if nn equals name, then we go ahead and return the environment without it. Otherwise, we return the nn, vv, colon, or appended to what we get if we delete this name from the rest of the list. which is XS, and we still want to delete the same name. So then, to add a thing, that's actually really simple. So add env environment name value equals name comma value on the front of a list of the existing environment, but we want to delete any existing instances of that name first. Let's go ahead and call this delenv just so that everything has the same number of letters in it, because that's how being obsessive compulsive works. So we're trying to get env, so to do that we need the environment and the name. But the environment is actually a name, a value, and the rest of the list. And so there's two cases again. Well, get env of the empty list is an interesting case here. And what we're going to do here is just say that an unassigned variable, an undefined variable, has the value 0, because that's a reasonable default rather than throwing some error. But if there are things in the list, then we can say if the name that the user is looking up is equal to the name of the current thing that we're looking at, then we return the value. Otherwise, we look up the name in the rest of the list. So let's give this a try. Oh look, I renamed delete and I didn't actually change it in the two places I was using it. This is why we test code, because otherwise it's wrong. So, empty environment is the empty list. If we want to add a name and a value to an environment, we get a list with that mapping in it. We can add a second mapping, and now we have two mappings in our environment. And then we can look up, oh, let me show replacing something. So if I want A to be 6, looks like I get A 7, then I can make a third environment where A is now 7, because we deleted the old value and then put the new value on the beginning of the list. So then finally we can look things up in this environment with getEnv, the environment, and the name of the variable. And that does the thing that we want. Now this data structure isn't especially efficient if we have large environments, but we're just dealing with the calculator, so it will be more than fast enough. So what's the next step in adding variables to our calculator? It looks like the next thing that we need to do is maintain the environment in the redevelop print loop. We can do that. Come back here and find the redevelop print loop in the source file for the calculator. The redevelop print loop is implemented as two functions. This readLines function, which reads lines from the users, and then this evalPrint function, which parses and then evaluates and then prints the expressions. So let's just go ahead and put environments in here everywhere. First, we'll put an environment here, then we will want to go ahead and pass that to a val at some point, but we don't want to change a val yet, so we'll just pass it in at the end. And then here in readlines, we will throw an environment on the end. And then we have to throw another environment on the end here when we call it recursively. And then we have to throw an environment on the end of the call. So let's just make sure this still works. Looks like when you change a function, you have to update its type. And the way types work, luckily we're working in Haskell here, where it makes you actually figure out what your types are going to be, because otherwise nothing works. By looking at this, we'll realize that we need to actually return a value in a certain number of places. So we need the new environment when we call this function. We can say env prime, because that's convenient. And then we need to return a value from here, which we won't change because we haven't updated a val yet. And we also need to add an environment, which is a list of string and int to the type declaration for the function readlines. So let's see if that builds. Apparently it doesn't. So at line 68, the type of the function, which we explicitly declare, doesn't match what we're doing. So we need to go change the type of this function. This is actually a function of IO environment. So let's see if that works. Okay, that got rid of that error, and we have another error. So this error is in looks like we still don't have the type right in the eval print function, in that it doesn't know that it takes a environment as its second argument. Just for clarity, let's go ahead and throw this type line up here in eval print. So eval print is a function of two arguments. The first is a string and the second is an environment. This function can do IO and it returns an environment. Now when I type make, it'll give me a new error. Looks like when I'm calling something recursively, I didn't pass an environment. Well, not recursively. When I'm calling eval print, I'm not passing it its environment. And now that I actually have all the environments in the right place, if I run simple calc, it'll work. If I say a equals 3, it won't work because we haven't added variables to our eval function yet. But we have a environment so that we can pass it to our eval function and it will continue between multiple calls to it. So to handle evaluating variables, we need to add two cases. The name case, where we have to look up the name of the function, the name of the variable in the environment, and we need to handle the assignment case. And in the assignment case, what we're going to do is just say that the first argument, the left-hand side, is a name every time. And Haskell can complain at us that we have a incomplete incompletely specified pattern if we try to type some other expression on the left-hand side of our assignment. So let's just call the expression EE here and say equals. So what we see as the problem here is that we don't actually have an environment in either of these places, so we can't do assignment or lookup. That's sort of annoying. What it means is that we're going to have to pass the assignment or the environment around everywhere. So let's go ahead and do that. Every call to eval has an environment as its last argument. And that means all these recursive calls need to have an environment as their last argument. But now that we have an environment, we have a way to look up values. We can just do getEnv environment name. And assignment similarly, we can do addEnv environment name eval expression environment. So there's still one problem here. We've got an environment into the function, but we haven't come up with a way to get it back out. So to do that, we're going to have to warp our code a little bit more. Instead of eval being a function that takes a calc expr and an environment and produces an environment, and produces a value, we have to make it return two things. It needs to return a value, but it also needs to return the new environment, because we update environments in specifically assignments. So assignments need to be able to return both the value that the expression has evaluated to and the new environment after the update. So the return value of eval is now a tuple of the value that the expression evaluated to and the new environment, which means that every single one of these guys needs to return the environment. So figuring out how to type sum properly is a little bit annoying because we're going to have to pattern match. Actually, the same problem applies to negate here, because what we need to do is we need to evaluate we need the return value of this call to eval here. So we're going to say that this is equal to the new value, comma, the new environment, where the new value, where the value of evaling the argument and the new environment is gotten from evaluating the argument negation in the old environment. Let me see if I can say that more clearly. So, in order to calculate the value that we get by negating a expression nn, we need to evaluate that expression nn in the current environment, which will give us a new value nn prime and a new environment n prime. And then what we need to return is the negation of the value that we got when we evaluate nn. combined with the new environment that we got from evaluating. So for binary operators, this is even more complicated. We need to return the value of evaluating AA, evaluating BB, and adding them together, as well as the environment we get after evaluating both of the arguments to the addition. So where AA prime and N prime is eval AA env, and BB prime env prime prime is eval BB env prime, because we need to run the left half of the addition first in the old environment, and that generates a new environment where we then have to run the evaluation of the second argument to the addition, which will generate a third environment, which is what we return from the addition. This is in case we have an expression like A equals 5 plus B equals 7. Which is an annoying expression, but it's something that's legal in our language that we've put together here, so we have to handle it properly. So, luckily for us, the story for all of these other guys is basically the same. Except we need to, instead of adding, we need to do whatever the other thing is for the binary operator. So for difference, we subtract. For multiplication, we multiply. And for integer division, we call this div operator. So we still have to handle names, in which case the value is the getEnv, and the new environment is just the environment, because referencing a name doesn't change its value. But then for we have this question of what do we return when we do an assignment. I will just punt and do what C does. The return value of an assignment is the value being assigned to the variable. So we'll say where where the new value and env prime is what we get when we eval the expression in the environment. So then the new environment, the new environment, is what we get when we do this add-env thing on the new value. And we're doing this in the new environment that we got by evaluating the expression on the right-hand side of the equals operator. And now we have sufficient information to figure out what the return value of this case for the eval function is. And that's the value we're assigning and the new environment after we've both evaluated the value of this expression, the value that we're going to assign to the variable, to produce one environment, and then actually added the new name to that environment to produce a second new environment, which is the environment that we return. And assuming I typed everything correctly, which I didn't, everything would have worked beautifully. So The complication here is that I didn't update the eval_print function to handle having one more argument in the expression thing. That is relatively straightforward. So down here in eval_print, we will say that the new environment and the value are what we get by evaluating the expression in the old environment. And then we will print the value and return the new environment. Apparently, I just typed in completely wrong code in line 73. Let's see what it is. Let in. I have two let expressions here, so I can just do this, move down the in, line everything up, see if that builds. Surprisingly, that builds. I can say a equals 5. Then I can be like a plus 3, and 5 plus 3 is 8. I can say b equals 7 plus c equals 2 times a, and get the answer 17. And this should be 7, and a is 5, so 2 times a should be 10, so this should be 10, so that should in fact be 7 plus 10 is 17, and now b is 7, and c is 10. And that is how we add variables to our calculator program. So we did in fact pass the environment in and out of all the cases of our eval function. We set up the equals operator so that we could set variables. We set up the name case in both the parser and the eval function so we could read variables. And at this point, we have successfully added variables to our calculator program.